All right, it was a lot of work getting there, but finally we can define the area of a region in the plane. Let f be continuous and non-negative on the closed interval from a to b. So we have a function. It's a continuous function. Non-negative means that we're taking only the part that is above the x-axis. The area of the region bound by the graph of f, the x-axis, and the vertical lines from x equals a and x equals b is, all right, so again, we're finding the area, this pink stuff that's right here, above the x-axis, below the curve, in between x equals a and x is equal to b. Well, this area is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of c sub I times delta x. What? This is saying it's the limit of a Riemann sum. And that's exactly what the area of that plane region is. It's a limit of a Riemann sum. What's a Riemann sum? It is the sum of products and the two things that are being multiplied in those products, function value and a width. The function value gives us a height of the rectangle. The width gives us it's basically the width of that subinterval. How do we find that width? Well, if it is a regular partition, you use b minus a over n. If it's not, then you just subtract the two widths, or the two endpoints, I should say, x sub I minus 1 and x sub I. So the picture here uses c sub I for whatever x value you use to evaluate your heights. In a previous slide, we saw x sub I with a little star, which we pronounced as. So depending on the book that you're looking at, you're going to get some slightly different notation. So it just essentially means that you're evaluating your function at some x value in each one of those subintervals. And it really doesn't matter which one you use, left side, right side, midpoint, or anything in between. After you take the limit, you're still going to approach, you're still going to converge to the same value, assuming that the area actually converges to a number. We will see in another chapter, another unit, instances where that area just gets infinitely big, it diverges. Okay. But for this particular unit, they will definitely converge to a nice, neat number. And we will evaluate the number, find that number, using a limit of a Riemann sum. Let's do such a thing here on example 5. Find the area of the region bound by f of x is equal to x cubed, the x-axis, and the vertical lines x equals 0 and x is equal to 1. So we can see that we have our function. It's just the cubic function. And sure, not the entire cubic function is non-negative because you have another part of it we're just not seeing, but we don't need that part. We don't need that part because we're starting at 0 and going up to 1 right here. Right? And our vertical lines, x equals 0, x equals 1, essentially means that we're partitioning the interval from 0 to 1, sort of like we did for the parabola. Okay, so let's write out a limit that's going to give us the area for this plane region. So our area should be equal to the limit as n goes to infinity. That's the number of subintervals, which is basically the number of rectangles. And whoops, summation from n, not n equals, no, that's I equals 1 to n. And you need two things here. You need a function value, doop doop, and you need a width, our delta x, that's right there. Let's find the width first. Delta x, probably the easier part of this whole process. We know it's b minus a over n. Our b is 1, our a is 0 over n. Well, it's the same thing that we saw before. It's 1 over n. Who would have guessed? Okay. And then our function value. Remember that whenever we go to evaluate this, we can do it at any x value in each one of those intervals that we want to. Which one would you suggest? Did you say the left? Did you? Did you say the midpoint? I hope you didn't, because we're going to use the left, the right endpoints, yeah. Here, let me draw another graph for us, because the other one just wasn't cutting it. Yeah, so we would have part of our graph down there, but we're not going to use that part. Okay, we're using the right endpoint after we partition this guy, sort of like this. Right endpoints, right endpoints, right endpoints, and so on, dot, dot, dot. Okay, so for this first one, that is 1 over n, because our width here, we already discussed, is 1 over n. And then you would have a 2 over n. Is this looking familiar? A 3 over n, and so on. So in order to find each one of our function values, which corresponds to our heights, f of 1 over n, f of 2 over n, it's like deja vu up in here, 3 over n, and so on. And since we're using a right Riemann sum, we're going to go all the way up to f of n over n. Let's try to generalize this. This is what I get whenever I plug in I equals 1. This is what I get whenever I plug in I equals 2, I equals 3, and so on. And you can see that this is just basically I over n. So inside of here, instead of that question mark, I'm going to put I over n. That was supposed to be blue. Pretend that it is. Thank you. Okay, so now let's evaluate our limit here. Actually, before you evaluate the limit, you want to simplify this sum. Now, just to be super clear, the variable for the limit is n, but the variable for the summation is I, right? Okay, so keep that in mind. This f of I over n, and then this delta x we said was 1 over n right there. As we did before, we can take this, where's the summation symbol? There it is. Okay, we can take this 1 over n and we can take it out of the summation, but we can't take it out of the limit. Why is that? Because n is a constant as far as the summation is concerned, but it is a variable as far as the limit is concerned. So I will rewrite this as the limit as n goes to infinity, bring out the 1 over n, and times the summation from I equals 1 to n. And I'm just going to go ahead and plug I over n into our function, and our function was just x cubed. So we just cube this. I over n cubed. I over n cubed is just I cubed over n cubed. Okay, once again, I is the variable for the summation, but n is the variable for the limit. I can take this n cubed and bring it out to meet this 1 over n that's right here. Whoops, no. Limit as n goes to infinity, 1 over n to the 4th this time, sum I equals 1 to n of I cubed. I think that we have a formula for I cubed. Do you remember it? I know you probably made some flashcards for each of these, even though I told you not to. Okay, here it is. It is n squared, n plus 1 squared over 4. It's basically the one from Gauss, just squared. Why is that? I don't know. Did you do the summer assignment? If you did, you probably know. Okay. That's not me sounding bitter. I mean, if you did it, that means I had to grade it or, avoid grading it. The limit as n goes to infinity, 1 over n to the 4th, and this summation turns out to be, I'll put brackets right here, n squared, n plus 1 squared over 2 squared, which is 4. Okay. All right, and then we can do a little bit of cancellation. Get out your crayon. Cancel out this with 2 factors of n down here at the bottom. Is equal to the limit as n goes to infinity of n plus 1 quantity squared over 4n squared. Oh, we are finally ready to take the limit. So notice, if you will, that the degree of the top would be squared. It'd be n squared if you were to expand all this out, and the bottom is also n squared. Matter of fact, if you did square this thing out, it would be n squared plus 2n plus 1. Okay, so you can use a pre-cal rule in order to evaluate this limit. Leading coefficient here is 1. Coefficient down here at the bottom is 4. The value of this limit is 1/4. What did we just find? We just found that the area underneath f of x is equal to x cubed from 0 to 1, this area converges to 1/4 as we increase the number of rectangles, get closer and closer to infinity there, which is a fancy way of saying the area underneath the curve here is 1/4. Now, I know what you're thinking. The first thing that you're thinking is, surely there's an easier way to find that. And there isn't. I'm sorry. It is always going to be this complex. That's actually a lie. The second thing is like you're probably asking yourself, because you should be, why exactly are we finding the area underneath a curve? Because that seems like a strange thing for me to want to do. And I have to apologize for this. I'm not going to tell you yet. I'm going to leave it as a mystery for us to get a little bit more calculus in order to be able to connect all the dots. There is a very specific reason. It does have to do with inverses. It does have to do with antiderivatives. It does have to do with derivatives as well. All of these pieces come together in a nice, neat package. You just have to wait for it. Be patient. All right. So if there's some more time, I'll do some more examples for you. If not, I think that's pretty much going to do it for this lesson.